So we are from group 2, and today we will talk about power series, specifically Taylor and Maclaurin series and its application. My name is Liza Rizky Ramadan.
My name is Maclaurin.
My name is Safira Delina.
My name is Raditya Jiza.
And our other member is Dennis Erham, who unfortunately could not.
Now we're going to talk about the power series. A power series about A, or just power series, is any series that can be written in the form like this, where A and Cn are numbers. The Cn's are often called the coefficients of the series. The first thing to notice about the power series is that it is a function of x. That is different from any other kind of series.
Hello everyone, my name is Maclaurin, and I'm going to explain about the first topic, that is the operation on power series. And there will be 3 subtopics that I'll be explaining. The first one is addition and subtraction. If there's 2 functions and it is being decomposed into power series with the same center C, the sum or difference of the function of the power series can be obtained by addition and subtraction. We can see that there's equation for fx and gx. Since it both has the same definitions, we can just merge it together and it becomes one equation. The second one is multiplication and division. For multiplication, if we have 2 equations being multiplied to each other and both equations has the same definition, we can merge it together, but the power of x minus c is being changed into the addition of both a and b values. For division, the simplest explanation is that if the sequence Dn is defined with the equations, then fx is the result of the division equations times the gx. And by comparing coefficients, it can be solved recursively for the Dn terms. The third one is differentiation and integration. In here, we differentiate and integrate by treating every term separately. We can see that we integrate the equations and then the n power of the equations are dividing the equations. After that, we give it plus k at the end. Both of the series have the same radius of convergence as the original one.
Okay, so now I'm going to explain to you about the example problem of a power series. So the problem here is to determine the interval and radius of convergence of the following series, which is this one. First, we are going to start with the root test. Now we're gonna want to write it. We're using the limit of n approaching to infinity for this series. From this, L will be infinite. This is provided by the x is not equal to minus 17/2, so the series will diverge for this particular value of x. Also, we know that the power series will converge for x equal to 17/2. This is the value of a for the series. The interval of convergence for the series is x equal to minus 17/2, and the radius of convergence, or r, is equal to 0.
So basically, what we need to understand is that Taylor and Maclaurin series, in its most basic idea, is a way to find or give coefficients of x on a series of functions given their standard value of the function. So let's assume there's a function of fx, which is a series n equals to 0 to infinity, Cn x to the power of n. So the center of the function x is 0. So now what we're going to do is differentiate fx into higher derivative by using term-by-term differentiation. After that, we will put the value into the function. f0 equals co, f prime of x, c1, and while f second derivative to c2, and so forth. So now you can see there's a pattern here, which can be simplified into fx equal n factorial cn.
Next, I'm gonna talk about Taylor series approximation. A Taylor series approximation uses a Taylor series to represent a number as a polynomial that has a very similar value to the number in a neighborhood around a specified x value. The polynomial for the Taylor series approximation is fx equals f a, the function of a, plus its first derivative over 1 factorial times x minus a plus the second derivative over 2 factorial times x minus a squared plus the third derivative over 3 factorial times x minus a to the power of 3, and so on and so on. The Taylor series are extremely powerful for approximating functions that can be difficult to compute, as well as evaluating infinite sums and integrals by recognizing Taylor series.
Okay, in this video we're gonna talk about Taylor and Maclaurin series. And this is stuff that you can definitely spend a while talking about, so I'm gonna try and give you the 10-minute brief synopsis here. The idea is that in certain cases you can do this all the time. The idea is that you can rewrite a function fx in terms of an infinite sum of other functions. And basically the formula that you need to know generally is this. The idea is you're gonna center this, what's called some value a. So it says we write fa plus f prime a times x minus a to the first over 1 factorial plus f double a times x minus a to the power of 2. Over 2 factorial, these patterns keep continuing, the derivatives get higher, the power get higher. The factors get higher, and this keeps just going on and on over. And just more compactly, using summation notation, it says we can rewrite that as the infinite sum. On the nth derivative evaluated at a x minus a to the nth power over n factorial, the only thing you really have to fill in on this formula is you have to calculate fa, f prime a. You'll drop in your given a value, fa, again you'll drop in your given a value. So on and so forth, so mechanically they actually turn out to be not so bad to calculate. You know, taking derivative can be tedious, sometimes they want to rewrite in the summation notation. That can also be tedious, but the basic idea isn't really too bad at all. It is one of these things that seems like it feels worse than it actually is. So let's do a problem. So we're gonna find what's called Maclaurin series for fx e5x. A Maclaurin series means that you're centering this at the value of a minus 0. In the other problem, it said we basically needed to start calculating derivative and plugging in this value, so I'm just gonna make a little table of derivatives. The first derivative, I'll get e times 5x times 5 or 5e 5x. The second derivative I'm gonna get, well, I'll get 5e 5x times 5. You could write that as 25 one thing. I also recommend is not multiply things out cause you'll see the pattern better. You can write as 5 square e to the 5x. The third derivative I'm gonna get 5 cube e to the 5x, and then general my derivative after I've done. So arbitrary number, I'll have to 5 to the n times e to 5x. Now all I'm gonna do is just fill in the formula with given values. So it says fa in this case will be f0. If I plug f0 into this, I'll get e to the 0, which is 1. f0 I'll get 5 e to the 5, or just fo I'm get square f0 I'll get 5 cube. Eventually my derivative evaluated at 0, I'll have 5 raised to the n power. Now if you compare this to the formula that I just had, it says we can actually write e to the 5x. Well, maybe we're not gonna talk about the justification for when you can or when you can't in this video. It says you'll get f0, which is 1, plus f prime over 0, which is 5. Then it says we take x minus our a value over 1 factorial. Then it says we take f double 0, which will be 5 squared times x 0 squared over 2 factorial. And we'll just keep this pattern up indefinitely. You could actually rewrite this a little more compactly. It looks to me like the infinite sum from n0 to infinity. We'll have then derivative, which is gonna be 5n, and then it simply looks like we have xn over n factorial. Notice if you plug in n equals 0, you'll get 5 to the 0. 0 factorial is defined to be 1, and so we'll get 1. If you plug in n equal 1, we'll get first term. If you plug in n equal 2, you'll get our second term, and if you get 3, and you get third term. Now this all considered a Maclaurin series expansion for the function e of x. This is usually what they'll want to see, a kind of more compact way of writing it. And then the problem could say find the radius of convergence or the interval of convergence, and we will simply do the ratio test on this. So if you're not sure about that, I'll talk about the ratio test and finding intervals of convergence rather of power series, and you can do all that stuff on this one.